Hi, Professor.
Yes. Welcome, Kevin.
Hello.
Hello, how are you? I need your topic for FISP.
We already decided upon one for in the email, right?
You haven't decided?
No, we already decided, right?
Oh, I missed that. I'll search my email.
It's the linear periodic system and periodic control, right?
Oh, Kevin, yes, you are. But I'm saying how you.
Oh, wait. What do you mean?
How you?
I'm doing fine.
Yes. I initially want to do that, but Kevin already did that, so I'm choosing maybe.
Yeah, you can send me an email
Okay,
about
yeah.
your options.
Okay, yeah.
Very good. So we are today in the week 13, lecture A. So today we are going to do something very mathematical and very practical. It's regarding pole placement. Okay, pole placement. So let me give you my screen here so you guys can all see it. Yes.
Mm-hmm.
Let me minimize it. Maximize this. I'll choose my ink as red, and I'm doing okay. So let's go. Looks like we are going to do FISP, and we'll have no final exam. So and today we are going to have a 1 hour session on PS8. So last time we briefly did the state feedback and talking about some definitions and the concepts. We learned that the state feedback will not affect controllability, but it could, okay, it could affect observability, okay? So we have seen this already. So at this point, I want to remind you another term I told you multiple times, I'm going to say again, called stabilizability. Stabilizability. That means everything we talked so far is a minimum realization, and it is minimum realization, of course, is a controllable and observable system. Okay, but sometimes when you work with not a minimum realization system, then you may have uncontrollable subspace. Okay, so no matter what you do, you will never affect this part. Okay, so it's not going to do that. So if this subsystem is unstable, then no matter what you do, you cannot stabilize the system. So then this system is not stabilizable fundamentally, okay? So therefore, to talk about stabilizability, okay? So like if you have A plus B, K, the state feedback, U is KX. So how you know that the K exists such that the overall system, closed loop system, is the poles can be placed in any place you want. So that existence of such K is relying on an assumption that the system is fully controllable and it's minimum. If we don't say minimum, then you simply say controllable is not enough. And you still have to say stabilizable. That is already implying saying that your C bar subsystem is stable. okay, is stable. Then the overall system can be said as stabilizable. So I hope I'm not confusing you. So let's move. Pole placement. So pole placement means you have state feedback. The whole state is available for you to do the feedback. So, but what if the full state is not available? Then we need to introduce observers. So in control, there are actually two steps, okay? So when you develop something, you say, oh, is this a state feedback? Still feedback control? Then you should say output feedback. So this, it turns out that output feedback is much harder, okay, than state feedback. So on the other hand, state feedback is the foundation. So you have to know this one first. So let's go to SISO, single input, single output case first. Okay, so you have a pole location important for the dynamic response of the system, cannot affect the zeros with the feedback. I already see that. So can we arbitrarily place the system poles? So these are the questions. The same thing we should answer for the MIMO system. So state feedback in the MIMO case. So for MIMO case, okay. So talking about, there are so many flexibilities in there, okay. So because of the MIMO, you have lots of feasibilities. This is a journal called Transacting of Automatic Control. It's a #1 journal in control. So here's the problem statement. So we have a desired pose, lambda1 until lambda n. So we define the P of S is open loop characteristic polynomial. This, okay. We're talking about SISO case right now. Okay. So then this is a polynomial of P of S, and with the highest term with the coefficient is unit. So this type of polynomial has a special name. It's called monic, okay, polynomial. Okay. So without, so these coefficients, okay, is the open loop, okay, open loop coefficients, okay. So let's say closed loop characteristic polynomial. Then we do this as a minus bk. So in fact, we are trying to use a negative feedback, okay, minus kfx. So, but if you say I want a plus, that's okay. It doesn't matter, okay. So that is a closed loop characteristic polynomial, and I have a desired characteristic polynomial. That is actually this one actually have a notation called pi is I is 1 to n lambda minus it's called S minus lambda I. So this is a kind of a notation. The 1 pi is a product notation and sigma is a summation. So we use alpha bar here as a desired coefficients, the coefficients of the desired characteristic polynomial, okay? Again, this everything is monic, okay? It's monic polynomial, okay? So I want this, okay? So this is an open loop, closed loop under K. Okay, giving a K, you have different Q. So can you find a specific K such that These are the same. Q is a closed loop transfer function. Characteristic of polynomial is a closed loop. So this is actually dependent on K, okay? And this is desired, okay? I want you to put, it's called desired. So this is should be comma K because K is your choice, okay? So the question is find a case such that this is true, which is obvious. Again, we are using minus kx. It's a negative feedback as u. But you can define plus here. Doesn't really matter, okay? So there's a theorem saying that if the original SISO system is controllable and can be arbitrarily assigned by the slave feedback, you can always do it. But the question is, what's the fastest way to check the controllability of SISO system? What is a typical uncontrollable SISO system? I give an example, okay? So if you have a system like S plus 1, S plus 2, so this is controllable, right? But, yeah. But if you have S plus 3, then here you also have times S plus 3. This is kind of get canceled out. So this pole at S minus 3, actually, you cannot change it. Okay, you cannot arbitrarily change that position. It's canceled out. Okay, so that's you are fortunate it's stable. But what if here is negative? Okay, so then this system is what? Not stabilizable. Make sense? Because that position cannot be changed. It's plus 3 in the right half plane. You cannot change it through feedback. So it's not stabilizable. So I just gave you a rough idea what an uncontrollable SISO system look like, because it's a cancellation of a stable pole somewhere. Okay. So the controllability is necessary. Okay, necessary. Okay. Otherwise, there is a pole that cannot be moved. Cannot be moved. Well, in what situation it cannot be moved? When? So answer is when it was cancelled by a pole or by a 0. Okay, make sense? Yeah. Okay, so how you prove it? Let's see. System are in the standard controller form. Show the controllable system can be transformed to the standard controllable form. Use these results to construct the feedback gain for an arbitrarily controllable system. So standard form. So we know it. This is our standard form. So this is alpha is my what? Is my open loop system, okay? Open loop system. So closed loop system, then I'm going to have BK because my B is only here, okay? Only here, the last one. So this is to me is like a chain integrator, okay? So I hope you will visualize chain integrator. So basically you will have something called x1 is x1 dot is x2, x2 dot is x3, right? So it's a chain of integrators, okay? Until the last one has a control of one UT here, plus equals xn dot, okay? So you have a minus alpha 0, x1, and okay? So So that's why I can recognize this is this. Sometimes people write in minus 1. Okay. Okay. So it's a chain integrators. Okay. Then closed loop without reference. Without reference, what does that mean? The reference is 0, so your origin is your equilibrium point. Okay. In other words, I hope after everything, then x infinity is 0. Okay. So when time goes, then we can talk about when this is not 0. It's okay by shifting, doing a variable change. So with this k, we can assign anything we want. But what if you have a reference like a BRT? This is called desired closed loop system without a reference. Then you have this one. Okay. So then your control objective is to bring your xt to 0. Okay, to 0, to equilibrium point as t goes to infinity. And how they like in 2D system x1, x2, how they get to the 0 in here, x2 here, it is always exponential decaying. Okay. So it is not only asymptotic, but also exponential, stable. But as we write design, this is desired. Okay. So if you have a reference, you just add in there. This doesn't really matter. So then your x will go to R. Okay. So this actually can pick state feedback k. You can. So this is called a proof. After you finish the proof, you actually constructed a way how to pick the k. So this process is called constructive proof. Constructing proof. Okay. So then you can construct the k through that. So this is the original coefficients. This is the desired one. So then the difference is the k. So you put this one in, so these two will be the same. Thus, this is true. Okay, done. So we can place the pose of controllable SISO system in standard controller form at the desired location arbitrarily. Okay, arbitrarily. We should say, arbitrarily. So then you can transform the controllable SISO system to standard form. Given the system, okay, you get this characteristic polynomial. Then you have the coefficients, okay, monic polynomial here. And the standard controller form is exactly like this we have learned before. Okay, so this is standard controller form. Why they write x hat? Do you guys have an idea why they do this?
Is it a unit vector?
Do you have an idea? Because original x, you need to do a coordinate transform to get into this form, standard form. So you need to construct the transformation. It's usually a similarity transform, so that you have a similarity transform queuing here. So, make sense? That's why you are under different coordinates. So then suppose P is Q inverse, and then this is we can write. So this is let me see. So this is original. Open loop controllability matrix, and multiplied by this form. Okay, by this form. You can construct the P like that. And this is the characteristic polynomial coefficient of original this original system. This one here, original in the original coordinates. You have alpha. Then what do? You construct this. But if you want to see how this is true, why this construction is true, the Jim Bay's book has a proof on this. Okay, has a proof on this. We're going to look into the literature later. Okay, so we don't get into this for too long, and we are going to work on this after the end of the lecture today. It's page 326. Okay. This person is called John Bay. Okay. He has a very nice state space textbook, but Magnify Lti system. So we assume this is written as a U times V. Okay. It's invertible because this system is controllable. Why? It's a full rank, all right? It's a full rank. This is also full rank. So because this construction, do you guys roughly know the stuff like this? So you can see this is the same, this is the same, this is the same. This matrix format is called Topliss matrix. This is a special Topliss matrix, okay? Topliss matrix. I think in one of the lectures, I derived this thing for you in terms of FIR response. Determinant is 1, so both of them are invertible. Therefore, P is invertible. So you get the inverse of Q. So you have this one. So how you can get out the A hat? This is the original A. This is the A hat. Is that standard form? So that's A hat. That's B hat. So this is very elegant and beautiful, right? So because we are talking about SISO output equation, and so what is this format? Okay, or this format of the numerator is the numerator polynomial coefficients of the transfer function. So left for student. We have learned this before, right? So because A is a special form, B is a special form, but C would be the coefficient of the numerator polynomials. So this procedure works for MIMO system if it's controllable from the first input. Okay, MIMO. So now we got a taste of SISO system pole placement. If it's controllable, then you can arbitrarily place the poles at desired location through that procedure. Okay, mainly through the controllable standard form. Okay, but for MIMO, we have very similar results. So it's true that you have to be controllable, then you can arbitrarily, so this is very important, arbitrarily assigned by state feedback and to make the closed loop stable. You can arbitrarily assign that. Achieving desired pole location isn't as satisfying for the MIMO system, okay? Why? Because that not like SISO, okay? That's in the SISO. So in the MIMO case, it's not like adding together and the multiple n SISO system. That's wrong idea, okay? So there is something called coupling, okay, between the subsystems, SISO systems, okay? So here in math languages, response is not only dependent on eigenvalues, but also the directions about eigenvectors that's contain all the couplings. So therefore, so you achieve a desired location in usually is not enough. Okay, but you know how to do it first. Then we talk about whether this location is good or not. Okay. So what is a good location? So that's the point. Good locations, when they are good locations. That's a separate question regarding design performance issues and especially on optimality issues. So they said, you give me desired location, I can achieve that desired location. But another layer of question is how these desired locations were decided. Okay, that's a design question about performance driven and could be robustness driven. Okay, so there are two questions: optimality and robustness. Okay, so these two will drive how you choose good locations. Okay, but that's a separate one. We probably don't talk about this too much. However, in the LQR part, we are going to address this a little bit by talking about linear quadratic cost function, such that this will actually define some good locations and you can achieve. That's a topic for next week. Okay, it's although everybody say, "Oh, LQR is easy," but it's kind of I hope you see the logic flow here. It's answer the question about what are the performance optimality issues here. Fortunately, in LQR design, the simultaneous also addressed the robustness issue. So it's very interesting, very beautiful. And so if we only care about time domain responses, so it is actually because of this coupling issue. So you cannot simply use pole location to answer this response performance issue. So in other words, even if you can place the pole at the desired, so-called desired locations, your response, okay, could still be very bad, because the response is not just pole locations. Also, surprisingly, depends on the zeros of a multivariable. Okay, not so long time ago, this topic, multivariable zeros, are still topical research. And even in the robust control course, ME 2012, we spent a long time talking about multivariable zeros. Okay, but I'm sure I don't have enough bandwidth time on multivariable zeros. But you just know that here the philosophy for MIMO pole placement, even if you put all the poles in the desired pole location, you cannot guarantee a good response, because response depends on not only the eigenvalues and eigenvectors, but also depending on the multivariable zeros. So this is a little bit surprising. But I hope the linear multivariable control multivariable, we should have a multivariable thinking. Whenever you have a multivariable thinking, you should always believe that all this couplings between all the state variables, okay? Because the matrix A is never diagonal, okay? So what I'm doing here. So the matrix A is never diagonal, okay? And even it has a property called diagonalizability. Diagonalizability. So if you have Jordan blocks, remember, okay, and you have geometric multiplicity and algebraic multiplicity of eigenvalues. So the A matrix may not be diagonalizable. That also means if it is not diagonalizable, that means it's not able to decouple it to become an independent SISO systems. It's not possible, isn't it? So MIMO is much harder. Okay, that's why you have a dedicated linear multivariable control. From this point, I want to emphasize on this. So let's achieve a pole placement. Probably is only the first step. There are many other things. So basically, we can use the same algorithm. So if controllable from first input. So you can do shuffle the states, shuffle. You can shuffle it so that you make the first input by the state transformation. If it was not in the first input, you can just put in the first input. It is controllable. Okay, so it's very interesting. Only need the first one to be a controllable. So question is how to best use degrees freedom added for those multiple inputs. Okay, that's a very good question. So there are more requirements you can add on this. Okay, add on this. So that is a paper addressed in here. We're not going to go that detail. So that's for state feedback using a pole placement. In the end of the slides, I'm going to show you a set of MATLAB commands that can do a pole placement automatically for you. Okay. So what if all the states are not available? Okay, not available. So then we need an observer to observer. That means X is not, so the K, so you have to have the X multiply the gain, then construct the U. But if there is not available, you have to have an X hat. You can use this estimation, okay, estimation. So how to estimate based on what? Based on Y, based on U, your input output. So let's see officially, what if not available? You can do the estimation. So then observer, you sometimes call it reconstructor because you are trying to reconstruct the state from available. This is available information, Y and U. So it's called X hat, okay? And then we can use the X hat that generate the control. So that's our state feedback, okay? So that's this, I hope you understand. So from this one, basically you can see this is the input to here is U, here is Y, okay? So this is Y. So based on U and Y, you generate X hat. Based on the X hat, as if you have all the measurements of the full state. So, because we are going to do partial state in a minute, next lecture. But now let's add a distinguish about this question is because you cannot assume none of these are available, so you need to reconstruct all of them. But what if you have a part of the X is available, part of X? So from here to here is available, from here to here, N2, they are N1 plus 1 to N. So this is not available. So you only need to reconstruct only part of it. So make sense? So we are now assuming all of X are not available, not measurable. You cannot measure from here. You don't have it. Okay. No. Okay. is not physically possible sometimes, okay? So therefore, math is important that you can make all these x reconstructed from x hat, in a sense that you should say x hat t goes to xt asymptotically as t goes to infinity. So in that sense, okay. All right. So this is called observer-based control. Observer-based control. And also here you can say, oh, actually, I merge this controller and estimator together as my controller. Together as my controller is called observer-based control. Okay, observer-based control. That's fine. So you can this shaded area is called this yellow shaded area is called actually your control, closed loop controller. So it's open loop. It's open loop is like a GFS. This is a CFS. Okay. So of course this is a MIMO. Okay, in the MIMO. Okay. This is also a MIMO. Okay. So that's separation of open loop versus your estimator and the controller here. So what do we want to achieve? So, okay. So I'm going to come back to my two questions about controller design is what do you want? And what do you have? Okay. Now in the observer design, I also have two questions, the same. What do you want? So would like, oh, I would like. So I want this state and estimate the same if all data are known, okay? Estimate approach to the state. Otherwise, you have stable error based on the state observation and the quantitative evaluation of error. So you know what's the error. So we're usually using an error is x t minus x hat t. Okay, so that's the error. Okay, called observation error. Okay, observation error. So let's go a little bit. So this is open loop system, and I have this is measurable. Of course, this is also because you apply this one to control the system. You have this information. This is what you have. Okay. So what do you have? And also you have ABC exactly. Okay. So these are what do you have? What do you want? I want x hat. Okay. Okay, and I want this x hat will be eventually the same as my x. Okay, we are talking about LTI. We know the U of t and ABC. This is ABC. This is a known. We know the input U. No fit through, meaning the D of U here. Okay, we don't have this one. Okay, so this is called direct feed-through term. Okay. Results are valid if presented with the derived output. So if I have DU here, so simply we redefine output Y like this. Okay. Then we discuss without D. So it's not a big deal. So observer structure is look at this. So there are two parts. The first part is make a copy of original dynamics. Okay. So this is make a copy of the original dynamics. Okay. If L is 0, okay. So that depends on the initial error. If this initial guess is the same as my original true state, if you set them the same, then of course everything will be the same because I'm running in parallel with the original system, make a copy of it. But you don't know x, t. So you also don't know what's x0, okay? Therefore, this is not a realistic assumption, okay? But if L is not 0, we can asymptotically make. So if not 0, it's still true. This is still true, okay? Still true, okay? So let's talk about feedback of observation, meaning, so the second term in here, this is a kind of called a prediction of my y hat. Based on my estimated x, then I know what is the estimated amount of my y. But this is my really measured actual system known output. So there must be a difference. I added the difference on to correct my x, okay? In a way that I choose the L properly. So how to choose the L properly? Such that my xt hat will xt. So that's dependent on the L. If L is not chosen properly, that's a problem. So Cx hat is a y hat, okay? The construction of the measurement, if estimate is state, so then term EY, so this is measurement error, prediction error. It's called also this prediction error. Because you basically estimate your x, so you based on that you can predict what is your y. Okay, c times x. So then the difference is EY. So EY has a name called prediction output prediction error. Between the true measurement, the y is the true measurement, and this is estimation of the measurement. Okay. So that's one term. Another term is L times EY. That's feedback of error. So we use this arrow in the difference between true measurement and estimation of measurement. We have EY times a gain here. Okay, and this need to be properly chosen. And then feed this one back the correct through this differential equation so that I correct it. So it's called propagation of estimation using system dynamics. So these are the same. So the system dynamics, I propagate it. So estimate remains equal to state if it is ever equal. Once it's the same, it will be always same, okay? So if they are not, so then we correct that estimation. So the question is, will this one work? What is the aerodynamics between state and estimate? So x and x hat, the error of it. They use a EY, probably they can use a EX. Okay. So let's do estimation error. They did a E, okay? They did a E. Estimation aerodynamics will be a DED. So this is true. So if you feel this is hard to swallow, you just using this one, and you have another one here. Remember, E is true minus estimate. So my true will follow my DDX. X is AX. So this is BU, the same, okay? Nothing else. So if I use 1 minus 2, I'm going to have DTE is AE. This one cancels out, okay? So I have minus L what? C times E, because this is CX, this is CX hat. So pull out the C, you get this one. So L times, so you have this system, and it's here. Cancel out, yeah, you have LC here. So this is a E, okay? This is another E. So that's my dynamics here. So whether E will go to equilibrium point 0, it depends on the eigenvalues of this one, right? Okay, eigenvalues of this one. And so you have a freedom to choose the L such that this is stable. Okay. Then you may have eigenvalue position, and is it possible you can arbitrarily assign the pole positions by choosing the L here? Pole placement, possible? That's the question. Okay. So initial conditions, they may not be 0. Okay, they may not be 0. So the aerodynamics will give you this one, and this is nothing input, it's just a homogeneous system without control, it's unforced. Unforced. Sometimes people use a homogeneous system is to say this is unforced system without input. So in this case, eigenvalues governs the response. Stable aerodynamics is Hurwitz. So all poles on the open left half plane. So, but we know A and C, and we can select the L. But the question is, can we find out does there exist such an L? At least you can choose one. Maybe the choices are empty. So there must be something there. Okay, so you can imagine what we want here. So estimation, you can say is observe. We are trying to observe X. No. We are trying to observe X, weird X hat, and this one is based on input and Y here. So this is a signal flow. So basically, you said we are trying to observe the X, okay, reconstruct X, and in the end, whether we can do it or not, is connected to eigenvalues, pole locations, eigenvalues of this matrix. Arbitrarily replaced. The condition is the AC pair is observable. This is beautiful, right? Yeah. So if AC is observable, then we know that A transpose, C transpose is controllable. We have learned this one called dual system, right? Dual system. Okay. So as if you write something like Z dot is A transpose Z plus C transpose U. This is a controllability. This is a controllable pair. Okay. So AC observable pair, then the transpose of this is controllable pair. So if matrix H makes this one here has eigenvalue with set of A, so we can then just choose L is H transpose, then you transpose back. Okay. So that connects to the previous discussion about pole placement and controllability. So in other words, if AC is observable, then this is controllable. If this is controllable, this matrix eigenvalue can be arbitrarily placed. So if you set this one, then the transpose of the aerodynamics matrix didn't change. So it's the same. So matrix has the same eigenvalue as its transpose. Okay, so A minus LC has desired eigenvalues. Arbitrarily, okay, arbitrarily. So that's called state estimation. I hope you guys can capture what we just said on this. Dynamic output feedback. So usually, so we can just combine. I put a circle previously in here with estimator is a k, x hat, and x hat has dynamics inside in x. So in this case, the controller C of S is not a static gain anymore. You need a dynamic system, dynamic controller, not a static. Okay. So that called dynamic output feedback. Okay. So this is a U, this is a Y, this is a disturbance. So control is static feedback. This is static feedback, okay? Static. For the X hat. However, X hat has a dynamics. So let me draw something here. So you have in here. This is your dynamic control. So it's no longer KX, it's like a K, like let's use C I J S matrix, then it times Y, okay, times Y. This is Y. So from here to here, that's actually, I'm using a CIJ of S. Of course, you have a realization of a state space form. So, but from signal flow point of view, so you got a U come over here. You get from this red box point of view. So you have a U and a Y coming in, coming out at X hat. Okay. But inside here, you have a BU. This is the same structure I have. And here we have feedback, LC, okay, minus LC, okay, minus LC. So this is a summary of a block diagram of an observer-based state feedback, okay, or output feedback. Okay. So this is an open loop system, and everything else is a dynamic controller, okay, dynamic controller. So this is a dynamic controller. Okay, dynamic control. So the overall inside here is a MIMO in this yellow shaded block. It's a dynamic controller. Compared to previous ones, if everything is available from here, you only need to pull out this guy to K. It's a static controller, okay? Static controller. So you only have Y available. You need to introduce dynamic controller. And this dynamic controller, zoom in, you'll see a structure of estimator and a gain, okay? Together is called a dynamic compensator. So this is estimator. So I hope everybody can remember this type of structure, okay, this structure. So by equations, we write, this is original input-output system, state space realization of G of S. And then we are going to have here, yes, because CX is Y hat. We merge this one into here, okay? So this is my observer state space dynamics, okay? State space dynamics. So only the C is to be decided, okay? After that, you decide, okay, so this is your control structure in equations. So in augmented closed loop state, you say this A stands for augmented, okay? So you put original here, and this one is x minus x hat. Okay. So this is my state. So I merge these two and write together to see what's the structure of a matrix. So it turns out that I can write it like this. So basically, this is writing. This is something like writing x minus, so the x minus x hat. Okay, but this one is of course there's a full invertible and a full rank. So I'm going to write closed loop system. So D is like that. So this is called aerodynamics. So closed loop dynamics, we are going to write like this. Okay. So this is my U. Okay, this is my U. And the X hat itself, okay, we can add and minus, add and minus. So it's good. So add one of this minus, add this minus. So this is 0, okay? This is 0. But because of that, I can borrow this one. 1 is to this one. 1 is to this one. This is E, BKE. Okay. Okay. So overall, I can write XA is something like that. So because I only want to leave E in here, closed loop or system dynamics, closed loop. So I don't have U anymore, right? The U is in terms of X hat in terms of E. So in the end, I write this is XA. So we want to study the behavior of this system. Okay. So compensator transfer function, then what does that mean is from UI to X. So what is output? Is you have compensator, your output is U, okay? Your output is U, okay? And I'm going to find out the transfer function here, okay? So then output is U, this is output in terms of a state. The state is in terms of the estimated state, So this is, so Y is here, okay? Y is here. So I want to see what's the CIG here. So basically I'm talking about the transfer function I want to know in this picture, from Y to U here, okay? So from Y here to here, what is the transfer function? So I'm trying to say Y is input, U is output, okay? So Y is input, U is output, and here we have this estimated observer state. So by doing that, we know we can do closed loop system. This is A, SI minus A, so minus A plus plus, okay, plus plus. Inverse, this is like origin B, this is like origin C, so minus C. So that is basically GC is close. This is a compensator transfer function, C. That is a GCS, okay. Okay. So the question is, what is the GPS? G plant of S. So of course it is open loop. What is that? It's C SI minus A inverse times B. Okay, that's compared to this. So you cascade this together, you got a GC, you have GP, then you have this one, okay? Closed loop. Okay, so I hope this is not too much. And then what's the original states? So let's write in terms of augmented states, meaning x and its estimation. So then we write in that way because I already can write this way. I placed y in there and inside. So this is the y. So then we end up with the dynamics of my x. So then I can write. So this is my matrix. I need to study. My yt is here, xa, because it's not x hat. So x tiered is my augmented state. So then I basically I can study what is the property here. So how to design this observer-based feedback control system? So you have two things to decide. One is L, one is K. So obviously, if this is stable, if this is stable, then everything will be stable, okay? So you need to be able to place all the eigenvalues of this, and this is called union, okay? All of them to be on the left half plane, okay? Left half plane. So we can select the feedback gain K and C. So you have two freedoms here. K is freedom, C is sorry, L is a freedom. So there is a separate design, okay? Separate design. So in other words, you can design a observer and feedback gain in a separate way, okay? So state feedback gain and observer gain. So so I made a small typo here by saying C is a design variable. No, this is not true. But however, remember, some times ago, I told everybody about if you can design a C, okay, such that the system is observable, okay. So so this is called measurement policy. Measurement strategy or whatever. Because when you are facing a real system, sometimes you don't have an idea on what is the measurements. So you probably have an idea, have a flexibility about deciding the C as a design parameter. Okay, design parameter. So this especially important in IoT cyber physics system today, and you have a chance to do the C. So we can summarize up, and today we talk about pole placement and observers, and so you need to place observers into a desired pole position, and in the MIMO case, you have lots of freedom, okay? And so the observer design, we use the shortcut about dual system idea, so it's much easier. And then combine them to form the closed loop design, and you have a separate property, and you have a separate design of the gain. One is K, one is L. So in the state space control design, we have this is one slide of all the So all the needed commands. Okay, so I suggest you help and study about that. Today we only did one pole placement design. Okay, so this design algorithm is based on the IGC paper. IGC stands for International Journal of Control. And that paper I also uploaded to this week's folder in the notes. So there are other variants. So I think right now it's good for you to understand the pole placement, but there are many more like LQG, LQI. So I'm trying to cover them as much as we, and all the basics, especially the LQR and LQG. Okay. They have discrete versions. Okay. And for the pole placement, the article here I already put in our folder. The place is like giving A, giving B, giving, what is the P? Can you guess? P is the desired or the pre-specified location. Okay, pre-specified location. You do A and B, giving a P, I give you a K. Okay, so that's the eigenvalue position of the giving the eigenvalues here, so you can decide the K. So the algorithm behind is actually about 15 pages long, 16 pages long. But today it's already in the textbook, and we just receive all this. That would be enough. Okay. And for state estimation, there are more like common filtering. So what do we mean common filtering? What's the difference between common filtering and LQG here? So I'll try to clarify the next week. And I said I'm going to, oh, yeah. We're talking about what's next. So next time we're going to do partial state feedback, okay? Next time. Meaning I have partial states are measurable, but some of them are not, so you need to estimate. So it's called reduced order observer design. Reduced order observer design. That's our next time we're going to focus on that. On the other hand, I'm going to dig out this wait. Why John Base is, oh, it's here. Okay. I have the full book, but I don't want to give it to somehow scanned. I can give you some chapters. So they said it's a page 326. That's 160. 326. Yes. 326. Okay, it's here. So the reason I want to show you here is regarding similarity transformation. How giving a, giving a B, giving a C, how I can change the state coordinate system, have a similarity transformation matrix, how to construct that matrix to turn it into a controllable form, okay? So we have seen this thing, and ACBC is a controllable form. We have seen that. You can also do observable form. So this is one you can swap this one to this side. It doesn't matter. You can change that. So don't feel this is strange. Okay. So, but the question is how I can find out so giving AB in here, how I can find out similarity transformation. Okay, so basically this is original A and B, and how I can get AC and BC the controllable form. So they said, hey, let's assume our controllability matrix is a B, AB, and A and B. So this is a matrix. Okay, and full rank is controllable, of course. So you can write controllable form. It's invertible. We have a single input system here just for simplicity. Okay. Okay. So then we assume that the P inverse can be right something like last column is P, last row is P, and then P inverse P. So we know that something times this one is I. So then we can just do the math because everything will be 0 until P an square is 1. So then from there you can get matrix transformation. Okay, that is, you assume the U inverse is P like this. So then you do U inverse times B, you will make the B only the last one column is 1. So we assume this U inverse, the U itself is U1, U2, UN, and this is identity matrix. So then you are trying to make the U1, U2, UN right this way. So this will come to identity matrix. So implying that PAI UJ is if I is not J minus 1 is 0. If it is 1. So that's the case. And so in other words, if you do the transform, so this is a P inverse AP is here. Okay. We are going to get into the transform the states and end up with this one. Okay. So it's some argument. So you can see that original is A. How you can get it to AC? You got the U inverse and the U here. Okay, so that's the way you should do. And U inverse B, you already know that is BC. That's the AC. Okay. Okay. So giving this one and you can construct, giving all these derivations, you can start to construct the similarity transform. Okay, so here it is. This is B is a P matrix. So you write P tiered matrix like this because you do similarity transform. You get up this one. And so this is under similarity transformation. And we talked about model controllability and observability before. But this equation, they were not giving in that textbook. I thought they gave, but you have to probably verify yourself. This one. This is interesting derivation about how you can construct so this is U, this is V, okay? U, this is V. So then how to construct this similarity transform matrix P. Don't try to memorize this. So it's a fact. It's a beautiful format. Okay. So we are going to finish. So do you have questions? Then we can come back at let's say 6:05. How about that?
Okay, good.
So then we are going to stop the share and terminate this one. Then we're going to restart without recording 6:05. Okay?
Okay.
Yeah, okay.
Okay.
All right. Bye-bye.